Hello my dear students, I welcome again all of you on this 4Pi Academy, and in this 4Pi Academy we are talking about the atomic and molecular spectroscopy, and until now we have discussed all about the classical concept of this atomic spectra, in which we have talked about the Bohr hydrogen spectrum. Then we have discussed about the series and fine energy limit of this hydrogen and hydrogen like energy spectrum, and further we have discussed about the Bohr-Sommerfeld theory. And in this lecture we will relate the concept of this classical and quantum mechanics, and how the quantum mechanics it introduced the other some sort of the parameters which is generally known as the quantum numbers. And then we will discuss about the vector atom model, and in this we will discuss in detail about the space and spin quantization of electron, and how the value of this orbital angular momentum and the spin angular momentum when an electron it is passing from this magnetic field, and how these values of these two quantum number it is being changed. And then we will calculate or discuss about the total angular momentum which is dependent upon this value of L and S. And then we will discuss important questions related to this problem. So starting with our lecture, so let us discuss the major failures of the Bohr theory. So for example, the Bohr theory does not explain the fine structure of spectral lines and the intensity variation in them. So moreover, if you can say, this is limited to one electron per atom. For example, it is generally successful for hydrogen and hydrogen like atom, and it does not explain for the other atoms, so in which there are more than one electron which is present. So it does not tell us how electrons interact with the atoms, and atoms how they interact with each other, so in order to give the further properties what is happening within the matter. So the limitation of this Bohr theory, it is due to the limitation of this classical mechanics itself. So if I talk about the classical mechanics, which is based on the assumption that in any system of particles it is possible to measure precisely the quantities like position, momentum, velocity, acceleration, etc. Equation of motion that enables us to determine these quantities, and these assumptions, however, it is contradictory in the quantum mechanics. So it is contradictory due to the uncertainty principle. So this uncertainty principle, which becomes important when we talk about the interaction of electron at atomic level or at atomic domain. Now, according to this uncertainty principle, the position and momentum of a particle cannot be accurately measured at the same time. So what does it mean? The measurement of one quantity, it introduces an uncertainty into the other quantity. So therefore, classical mechanics, which assumes that both to have a definite value at all instants, so it is not valid for atomic domains. So this is the main reason, so we need to introduce the concept of quantum mechanics in order to study the more detailed mechanism of the hydrogen and hydrogen like atoms, and what is the intensity and what are the other parameters which is being changing. So this is the reason that the Bohr model, which was just a classical atomic model in which the quantization was not properly introduced, so which leads to a failure of that atomic models. So the success of this classical mechanics, it is mostly happen at macroscopic systems, where we are talking about the system so at large level. So macroscopic system, so the classical concept, it is concept at macroscopic systems. And when we talk about the quantities at the microscopic level, so then we need to introduce the concept of quantum mechanics. Now, the limitation of these Bohr models, it has been overcome by the de Broglie. So he provided a hypothesis in 1923 which is known as the de Broglie hypothesis. So what he said that according to the quantum dynamics, the particle, it can act as a wave while it is in motion. So he gave the relation, an important relation, which is known as h over p, where p is the momentum of the particle if that particle it is moving with the velocity v. So this new theory of this quantum dynamics and the association of the waves to the particles in motion, so this is generally known as the wave particle duality concept. So this further this theory leads to further applications, and the various scientists, they designed their theories, and this they have been get the Nobel Prize for this discovery. And so he said that the particle, it can act as a wave as well as a particle. So this lead to the concept of wave mechanics or the quantum mechanics. Now later on, this quantum theory, it has been greatly improved by Schrödinger. So Schrödinger used this fundamental equation of quantum mechanics. So he derived a differential equation of these de Broglie waves associated with moving particles, and he introduced a mathematical function that is known as the wave function. So I will not go in detail about the quantum mechanics because you are already taking this course from the other instructor. So this wave function, it is a variable quantity which is associated with the moving particle, and it is a complex function of space coordinate of the particle, and which is changing with time. So he derived the differential equation, so from this de Broglie wave hypothesis, and he introduced equation, so that is 8 pi square m over h square e minus v psi. So this is the time independent wave equation of Schrödinger, so which can explain about the wave dynamics of the particle when it is in the motion. So let us discuss so how this wave particle duality concept. So moreover, these quantum mechanics solve many of the problems which could not be solved by this Bohr-Sommerfeld theory. So one of the most important outcomes of this quantum mechanics was the concept of quantum numbers. So that we will discuss in detail in our next lecture. But before discussing those quantum numbers, I will discuss about the famous model which is known as the vector atom model. The various scientists, they have put their efforts in order to design this model. So like Schrödinger, Gauss-Smith, Pauli, Stern and Garlick. So they designed this model, and this vector metal model, it is based on two concepts. So it is based on the concept of space quantization and it is based on concept of spin quantization. So let us talk about the space quantization first. Now we know that the motion of single electron of hydrogen like atom, it has been confined to 2 degrees of freedom. So that we have generally studied that the particle or the electron, they are moving in elliptical orbit, and so that is generally the x and y plane, so that is having 2 degrees of freedom. So an electron orbit or energy state, it is determined by these two quantum number which has been given as n and k. So one is the principal quantum number and second is the azimuthal quantum number. So that has been used by the Bohr-Sommerfeld theory. Now if we consider the motion of electron in three-dimensional space, then this gives 3 degrees of freedom. So that is in three-dimensional motion. So it is something like a mosquito which is flying in air, so that can move along xy, it can move along y axis, it can move along z axis, that is having 3 degrees of freedom. So this leads to the necessity of 3 quantum numbers to specify these energy states instead of these 2 degrees of freedom. So quantum number, it does not affect the size and shape of this Bohr-Sommerfeld orbit, but it specifies the orientation of orbits. So with the introduction of these 3 degrees of freedom, so they introduced a new quantum number which specifies the orientation of orbits in some direction in space. Now when an atom which is placed in uniform magnetic field, then the fixed axis in space, it is considered along the direction of the magnetic field, and due to the magnetic field the plane of this orbit possesses about this magnetic field, and the orbital angular momentum vector generates a cone about this field direction. So it is something like this, you can see here. So this is the our electron which is moving in a orbit which is having 3 degrees of freedom, and along x-axis it has a vector that is known as the r vector, and along y-axis it is having a theta factor, this one, and along z-axis it is having this phi factor. So with this, when the electron it is moving in this 3 degrees of freedom, and it is generating something like a cone like structure. So you can see that when this projection it is something like this, so it is forming motion of a electron that is in this cone. So the position of an electron in these polar coordinates, it is being determined by these r, theta and phi coordinates, and so this give rise to certain discrete orientation of orbits. So this give rise to discrete orientation of orbits, so with respect to magnetic field, that is H. So thus the electron orbits, they are quantized in space and having some discrete energy value, and that's why this is known as the space quantization. So they are moving in space in 3 degrees of freedom, having some discrete energy value, and this is known as the space quantization. So these 3 degrees of freedom leads to 3 quantum numbers, so that is n, k, and the introduction of the third quantum number which is generally written as m. So here m is known as the magnetic quantum number. In the vector atom models, these quantum numbers n, k and m, they given by Bohr-Sommerfeld theory, they have been replaced by the new quantum numbers, so that is known as the n, l and ml. So these are, n is the principal quantum number, L is the orbital quantum number. So the L, which is generally also known as the K, that is known as the azimuthal quantum number. So this has been said by Bohr Sommerfeld. So with the vector atom model, so they gave the new name to this azimuthal quantum number, so that is known as the orbital quantum number, and ML, it is known as the magnetic quantum number. So magnetic quantum number, so which is changing the value of this L, so that's why we write it as the ML. Now the value of these three quantum numbers, so the vector atom model, so they given the value, so the N, it can have any value from 1 to infinity. The orbital quantum number, it has one less value, so 0, 1, 2, 3, so from up to n minus 1. So while the value of ML, it varies from minus L to plus L, 0, again 1, 2, L minus 1 to plus L. So these are the new values of this magnetic quantum number. Now according to quantum mechanics, the orbital angular momentum of an electron, it is given by the orbital angular momentum of electron, it is generally given by L, that is under root of L plus 1 H over 2 pi. Now the projection of this L, so the projection of this L, so on the direction of this magnetic field, so that is the magnitude is generally written as the Lz. So this is the projection of L along Z axis. So let me draw here the diagram, so how we can represent this. So it is something like this. So this is the nucleus, this is the electron. So this nucleus, it is, if the magnetic field is something like along Z axis, and this is the value of L, that is the orientation at some angle theta, and the value of this angular momentum number along, which is parallel to this magnetic field, that is generally known as Lz, and whose value is of the order of ml into h bar. So this L value, where ml, it is the orbital magnetic quantum number, so we can solve different values for different L. So let us say for L is equal to 2, so for L is equal to 2, the number of orientation of L, so number of orientation of L in space, so they are, we can calculate from value that is equal to 2L plus 1. So when L is equal to 2, so total orientation will be equal to 2L plus 1, so that is equal to 5 orientation. So the magnitude of this total angular momentum number, so this we can calculate, that is from L plus 1, so that is equal to under root of 2 into 3, that is under root of 6. So similarly you can see that for L is equal to 2, there are 5 values of this magnetic quantum number, which varies from plus 2 to -2, and they are having orientation at different angles. So they are making different angles with this value of magnetic field. So these angles, so they are having different values, so for each case. So similarly you can calculate the orientation when L is equal to 3. So in that case the orientation that is equal to having 7 orientation. So the magnitude of this L, so this can be given by 3 plus 1 under root, so that is of the order of under root 12. So in this space quantization of an atom, so the orientation of L in the space, it is quantized, and we can write the value of Lz, that is equal to L cos of theta, and from that Lz we know that is equal to ml h bar, and this L that is equal to h bar under root of L plus 1. So from this we can write the value of this cos theta. So the cos theta, it comes out to be ml over under root of L plus 1. So for a given L, you can write here, so for a given L, so ml is equal to having a value from minus L to plus L, and the value of under root of L plus 1, that is greater than ml. So what does it means? It means that the ml over under root of L plus 1, it is always less than 1. So it means that the value of this cos theta, it is having some finite value. So L can never be in direction of Lz. So the total angular momentum L, it can never be in direction of Lz. So you can find out, so far L is equal to 2, so ml has a value of -2, -1, 0, +1 and +2. So from that you can calculate the total angular momentum, that is h under root of L plus 1. So and on the other side Lz, that is equal to L cos of theta, so that is equal to ml h bar, and from that the cos theta angle you can calculate for different values of this ml, and it is -2 over under root 6 for ml is -2. Similarly it is -1 over under root 6 when ml is equal to -1. It is equal to 0 when ml is 0, and again so cos theta is 1 over under root 6 when ml is equal to +1, and cos theta it is equal to 2 over under root 6 when ml is having +2 value. So what does it mean? So for each orientation, so when there is a change in value of ml, so for each orientation the angle is different. The second concept which has been introduced by the vector atom model, that is the concept of spin quantization. So second is concept of spin quantization. Now, the Schrödinger wave equation, when applied to hydrogen atom, it results into three quantum number which we have discussed, that is N, L and Ml, for the specification of energy state of an electron. Now these three quantum numbers, it could not explain some unusual feature which has been observed in the spectra of alkali gases. So like such as in the sodium vapor. So what does experimentalist they observed in the alkali gases spectrum? So they observed that the wavelength, they have two lines of doublet. So for example, if we talk about the sodium vapor, so there are two very close wavelength lines. One is at 5890 angstrom and other is at 5896 angstrom. Now, why one monochromatic source of light it is having two different wavelengths? Now, in order to solve this difficulty, S. Goldsmith and G. Uhlenbeck, they proposed the new concept of electron spin. So according to this, electron has spinning motion. So what they proposed? They proposed that electron has spinning motion about an axis passing through center. There will be two states, one will be spin up state and spin down state, it has been proposed. Now corresponding to this, in 1929 the fundamental nature of electron spin, it was confirmed by Pauli's direct development of relativistic quantum mechanics. So in 1929, so Pauli found that a particle with the mass and charge of the electron must have the intrinsic angular momentum and magnetic moment proposed for the electron. So it has some sort of intrinsic angular momentum and some sort of intrinsic magnetic moment. So when the electron it is moving under the influence of magnetic field. So later these, it has been performed, or it has been made proved by Stern and Garlick experiments. So they said that the electron it acts like a magnet, and they proved the electron spin with the help of this Stern-Garlick experiment. So that we will also discuss in our next lecture. Now what they introduced, so they introduced that corresponding to spin motion of electron, so an electron it has a spin angular momentum. So electron has spin angular momentum, and which is given by S, that is equal to S plus 1 h bar. So where S is the spin quantum number, and from this spin quantum number we can calculate the value of this spin angular momentum. So if you look at this picture, so this says that the orbital angular momentum vector L can never be aligned parallel or anti-parallel to the applied magnetic field. So this is because the Lz must be less than the total angular momentum. So this we have calculated because there is some sort of cos theta which exists. Now if Lz is equal to 0, then the L is perpendicular to the magnetic field, and otherwise this value of angular momentum it lies on the surface of this cone. So this is we have studied so they orientation, so different orientation, so of these electrons, so they lie on this surface of this cone. So when ml is equal to 3, then they will lie somewhere here. So when ml is equal to 2, so they will lie somewhere here. When ml is equal to 1, they will lie somewhere here. So this figure, it shows that the vector L lies on the surface of the cone for L is equal to 3, and this upper cone, it is showing when the spin of the electron, it is having up spin or positive value, and this down cone for the same orbital quantum number, so it is showing when the spin, it is having down spin. So again, from this we can calculate the total spin quantum number. So the value of S, so that is equal to under root of S plus 1 H bar. Now S can have either a plus or minus 1 by 2 value, and the value of this Sz, that is the spin quantum number which is moving parallel to the magnetic field, and that is of the order of ms H bar. So where ms, it is called the spin magnetic quantum number, and it has two possible values. So the ms, it can have two possible values, that is plus minus 1 by 2. So for ms, that is plus 1 by 2, it corresponds to spin up, while ms, that is minus 1 by 2, it is corresponds to down spin. So the representation of this ms, that is along the vector diagram, it has two orientation. So one is, so if this is the direction of magnetic field, that is along z axis, so this will be the orientation of S. So when it is having up spin, that is having plus 1 by 2 value, and again it is when ms is minus 1 by 2. So again, if you try to find for different values of L, you can see that the values of these energies, so they lie in some sort of a cone. So they will make some sort of a cone. So this is something like the cone like structure you can draw. So the upper cone, it represents the value for positive spin, and the lower cone, it represents the value for the down spin. And from this, so the vector atom model, so which is sum of the space quantization and the spin quantization, so therefore the total angular momentum of an atom, it results from combination of orbital and spin angular momentum of its electrons. So therefore we can write the total angular momentum of one electron atom. So it is the vector sum of orbital angular momentum plus spin angular momentum. So similarly, like the orbital and spin quantum number, so like all the angular momentum, so again J, it is quantized in both magnitude and direction. So the total angular momentum, it is also quantized. So the magnitude of J, so that we can write as total J plus 1 over h bar. So where J is called the inner quantum number, so it can has a value of L plus minus S, or you can write it as L plus minus 1 by 2, because the electron, they are fermions having half integral spin. So corresponding to Jz, so that is the value of angular momentum along z direction. So Jz we can write that is of the order of mj h bar, where mj it varies from -j plus 1, 0, j minus 1 up to plus j. So it varies from -j to plus j. So where mj it is known as the total magnetic quantum number. So in one electron atom there are only two relative orientations which are possible. So when J is L plus S, so when the spin of electron it is up spin, so in that case the total angular momentum it has a value greater than L, and when the electron it is having a down spin, so in that case the total angular momentum it has value less than the orbital angular momentum. So what does it mean? So it means that the angular momentum of the atomic electron like S and J, S and L, they interact magnetically, so which is known as the spin orbit interaction. So these L and S values, they interact with each others, so which is known as the spin orbit interaction, or we also known as the spin orbit coupling. So these interaction between the L and S, they exert torque on each other. So these internal torque do not change the magnitude of the vector values of L and S, but causes them to process uniformly around their resultant A. So due to the interaction between this spin and orbits, so between the L and S values, so they exert torque. So torque is angular force, so they exert some sort of angular force on each other, so which do not change the magnitude of vector values of L and S, but causes them to process uniformly around resultant J value. So what does it mean? So it means that, so if the atom is in the free space, so that no external torque it is acting on it, then the total angular momentum J it is conserved in magnitude and direction. So the angle between L and S it would remain invariant. So when these electron it moves under the influence of the magnetic field, then the angle value between this L and S it gets changed, so with respect to change in orientation. So suppose this is the atom, so this is its spin orientation, so this is, so let us say this is the value of S. So if this we take the value of L, so the total value of J it is something like a bigger value, so this will be the value of J. So J is L plus minus S. So it depends what type of electron spin it is. So from this we can write J is L plus S. So therefore J dot J we can write L plus S, L plus S. So J square, it is something like L square. So magnitude of S square plus 2 L into S cos of L dot S. So from that you can find the angle between this L and S. So that is of the order of J plus 1 minus L plus 1 minus S plus 1 over 2 under root of L plus 1 under root of S plus 1. So similarly the value of this angle, it is different between L and J. The value of this angle, it is different between S and J. So the angle between J and L, so that we can calculate from J is L plus S. So S is J minus L. So therefore S dot S, that is J minus L dot J minus L. So S square you can calculate, that is J square plus L square minus 2 into J dot L. So 2 into JL, that is JL cos of theta. This we can write as J square plus L square minus S square. So this is J plus 1 plus L plus 1 minus S plus 1 over, so this 2JL, J is under root of J plus S 1 and L is L plus 1. So this give rise to a angle of cos theta, that is between J and L. So similarly the value of this angle between S and J, that will also be different and you can calculate. So in this today's lecture, so what we have studied, that this vector model of an one electron, so it can be extended to many electron atoms. So what does it say? So in the presence of external magnetic field B, the total angular momentum vector J, it processes about the magnetic field B, while L and S, they continue to process about the total angular momentum J. So the precession of this J about magnetic field B is what gave rise to the anomalous Zeeman effect and the hyperfine energy spectrum structure of the hydrogen and hydrogen-like atom. So this we will discuss in our coming lectures, how the values of this orientation, it is being changed under the influence of the strong magnetic field and under the influence of this weak magnetic field. So in order to use effectively this vector atom models, so there are some certain important rules so which must be considered, such as the Pauli's exclusion principle and the selection intensity and interval rules and the Landis G factors, so which are different for the spin magnetic quantum number and the orbital magnetic quantum numbers. So this we will discuss in our next lectures. So let us do some numerical problems so related to these today's discussion. So the first numerical says two possible orientation of S with respect to an external magnetic field, that is B along z-axis. So what can be the two possible orientations? No we have studied that the angle between magnetic field and the spin magnetic quantum number, so that is of the order of cos theta, which is ms h bar over under root of ss plus 1 h bar. So this get cancelled. So ms, we have studied the magnetic spin quantum number. It has either a plus 1 by 2 value, that is for up spin, or minus 1 by 2 value, that is for down spin, and the value of spin, that is 1 by 2 for electron. So putting these values in this equation, we can find the angle between this S and the orientation magnetic field. So this comes out to be plus minus 1 by 2 over under root of 1 by 2 plus 1. So that is of the order of plus minus 1 by 2 into 2 over under root of 3, that is equal to plus minus 1 over under root of 3. Therefore theta, that will be equal to cos inverse plus minus 1 over under root 3. So the correct answer is option B. So B is the correct option. So let us do the another numerical, so which says the angle between the orbital angular momentum, so that is the L, and the spin angular momentum S for 2d 3 by 2. So we have to calculate the value of angle that is between L and S. Now for 2d 3 by 2, so how we can study this number? So this is generally known as the ground state of a given atom, of an atom. So this we will discuss in detail in the coming lecture. So generally this we write it as the value of 2s plus 1, that is the total spin orientation d, and this represent the total angular momentum number. Now if you compare this with 2d 3 by 2, so 2s plus 1, the number of orientation it has 2, and from that you can calculate the value of s, so that is coming out to be spin, that is of the order of plus 1 by 2. And similarly j, that is 3 by 2, so j, it can has L plus S or L minus S. So here S is plus, so therefore j is 3 by 2, L is, we have to find S is 1 by 2, and from that we can calculate the value of L, that is 3 by 2 minus 1 by 2, that is of the order of 1. So cos theta, that is between L and S, so this we have already derived, so whose value is j plus 1 minus L plus 1 minus S plus 1 over 2 under root L plus 1 under root S plus 1. So putting the value of j and L and S, so in these equation, so this becomes, so j is 3 by 2 plus 1 minus 2 plus 1 minus 1 by 2 plus 1 over 2 under root of 2 plus 1 under root of 1 by 2 plus 1. So this is the value of cos theta between L and S. So cos theta L and S, this comes out to be 15 over 4 minus 6 minus 3 by 4 over 2 under root of 18 over 4. So this comes out to be, so this you can do with your own. So it comes out to be minus 12 over 4 under root of 18. So that is minus 12 over 4. This is 3 minus 3 over 3 under root of 2. So that comes out to be minus 1 over under root of 2. So cos theta ls, that is minus 1 over under root 2. From that we can calculate theta. So that is equal to 135 degree. So the correct option is option D. So this is all about for today's lecture. So in the next lecture we will talk about the 4 types of quantum number and how the value of this from this spin quantum number we can calculate the magnetic movement, electron magnetic movement of a nuclei, and how these magnetic movement, so it leads to change in frequency, change in spin of those electrons. So we will talk about the Larmor frequency precession of the electron, and then we will talk about the Stern-Garlick experiment, which has experimentally proved the existence of magnetic spin quantum number of electron. So all this we will discuss in the next lecture. So if you have any query for today's lecture, you can write in the comment box, or you can ask your queries, your doubts by leaving a message. So keep watching 4Pi Academy. So till then, goodbye.